The story of Earth's ice ages is the story of our planet's most dramatic mood swings, massive climate shifts that turn tropical paradises into frozen wastelands and then back again, over and over, in cycles that scientists are only now beginning to fully understand. These aren't just interesting historical events that happened long ago, they're part of an ongoing process that could return with devastating force, and understanding them might be the key to predicting and surviving our own climate future. If you find these glimpses into Earth's frozen past as fascinating as I do, make sure to subscribe and ring that notification bell because we're about to embark on a journey through millions of years of ice and snow that will completely change how you think about our planet's climate, and trust me, by the end of this, you'll never complain about winter the same way again. The first mind-blowing fact is that for the vast majority of Earth's 4.5 billion year history, there was no permanent ice anywhere on the planet, not even at the poles, making ice ages the exception rather than the rule. Earth's normal state is what scientists call a greenhouse climate, warm from pole to pole, with crocodiles swimming in the Arctic Ocean and palm trees growing in Antarctica, a condition that has prevailed for roughly 85% of our planet's existence. The very idea of a frozen world is actually bizarre when you look at the big picture of Earth's history, yet these rare frozen intervals have had an outsized impact on the evolution of life and the shape of our modern world. Earth has experienced at least 5 major ice ages, periods when large sheets of ice covered significant portions of the planet, and we're currently living in one called the Quaternary Ice Age, which began about 2.5 million years ago. When most people think of the Ice Age, they're actually thinking of the last glacial period, which ended just 11,700 years ago, but that was just the most recent cold snap in an ongoing ice age that consists of alternating glacial and interglacial periods. Right now we're in an interglacial period called the Holocene, a relatively warm interval between glaciations, but the ice age itself is far from over, and the massive ice sheets of Antarctica and Greenland are reminders that we still live in an ice age world. The earliest known ice age happened around 2.5 billion years ago, called the Huronian glaciation, and it might have been triggered by the first major pollution event in Earth's history when cyanobacteria began producing oxygen through photosynthesis. This oxygen reacted with methane in the atmosphere, destroying this powerful greenhouse gas and causing temperatures to plummet so dramatically that the entire planet may have frozen solid from pole to equator in what scientists call a Snowball Earth event. Imagine Earth as a giant cosmic snowball, completely white, reflecting nearly all sunlight back into space, with ice covering even the tropical oceans to a depth of half a mile or more, a condition so extreme that it's amazing life survived at all. The evidence for these ancient ice ages comes from distinctive rocks called tillites, which are basically fossilized glacial deposits, containing a chaotic mix of particle sizes from fine clay to huge boulders, exactly what you'd expect from rocks ground up and dumped by moving glaciers. Scientists have found these glacial deposits in places that were at the equator when they formed, proving that ice reached even the warmest parts of the planet during the most extreme ice ages. Some of these ancient glacial deposits contain drop stones, rocks that were carried out to sea by icebergs and dropped into fine marine sediments when the ice melted, leaving behind a geological calling card that says, "Ice was here, even in places that are now burning deserts." The Snowball Earth events were so extreme that they almost ended life on Earth entirely, with photosynthesis nearly shutting down globally as ice covered the oceans where most photosynthetic organisms lived. Life survived in small pockets of open water maintained by volcanic heat, or in cracks in the ice where enough sunlight could penetrate, or possibly in a thin layer of slush at the equator where the ice wasn't completely solid. The fact that life survived these global freezing events and then exploded in diversity afterwards suggests that extreme environmental stress might actually drive evolutionary innovation, forcing life to find new solutions to impossible challenges. What ended these Snowball Earth events was volcanism, which continued even while the planet was frozen, slowly building up carbon dioxide in the atmosphere over millions of years since there was no rain to wash it out and no exposed rock for it to react with. Eventually, carbon dioxide levels became so high, possibly reaching concentrations hundreds of times higher than today, that the greenhouse effect finally overcame the ice albedo feedback and temperatures skyrocketed. The end of a Snowball Earth event would have been catastrophic, with global temperatures swinging from -50 degrees Celsius to +50 degrees Celsius in just a few thousand years, torrential rains lasting thousands of years as the hydrological cycle went into overdrive, and massive carbonate rocks forming as all that CO2 reacted with newly exposed rock. The next major ice age didn't occur for over 1 billion years, during the late Ordovician period about 445 million years ago, and this one had a very different cause involving the position of continents and possibly a gamma-ray burst from a nearby exploding star. When the supercontinent Gondwana drifted over the South Pole, it created conditions for ice sheets to form, and once ice started accumulating, the albedo effect took over, reflecting more sunlight and cooling the planet further. This ice age coincided with the second largest mass extinction in Earth's history, killing about 85% of marine species, though it's debated whether the extinction was caused by the cooling, the sea level drop as water was locked up in ice, or other factors. After another long warm period, Earth experienced the Karoo Ice Age from about 360 to 260 million years ago, when the supercontinent Pangaea was assembled and partly positioned over the South Pole. This ice age is particularly interesting because it occurred while plants were first colonizing land in a big way, and the spread of land plants may have actually contributed to the cooling by increasing rock weathering, which pulls CO2 from the atmosphere. The evolution of trees with deep roots broke up rocks more effectively than ever before, accelerating chemical weathering that locked away atmospheric carbon dioxide in sediments, showing how life itself can trigger ice ages. Then Earth went through another long warm period, including the entire age of dinosaurs, when there was no permanent ice anywhere on the planet and sea levels were hundreds of feet higher than today, flooding vast areas of the continents. During the Cretaceous period, atmospheric CO2 levels were 4 to 8 times higher than today, palm trees grew in Alaska, and breadfruit trees grew in Greenland, creating a hothouse world where dinosaurs could live comfortably at both poles. The Arctic Ocean had surface temperatures of about 14 degrees Celsius, warm enough for comfortable swimming, compared to near freezing today, showing just how dramatically Earth's climate can change. Our current ice age, the Quaternary, began gradually as CO2 levels declined and continents moved into positions that favored ice formation, particularly with Antarctica settling over the South Pole about 34 million years ago. The formation of the Isthmus of Panama about 3 million years ago was a crucial trigger, shutting off tropical ocean circulation between the Atlantic and Pacific, redirecting warm water northward in the Gulf Stream, which paradoxically increased snowfall in northern regions. This shows how ice ages can be triggered by seemingly small changes in geography that alter ocean currents and atmospheric circulation patterns in ways that cascade into global climate change. The Quaternary Ice Age has been characterized by regular cycles of glaciation and deglaciation, with ice sheets advancing and retreating on timescales of tens of thousands of years, controlled by variations in Earth's orbit called Milankovitch cycles. These cycles include changes in the eccentricity of Earth's orbit around the Sun, the tilt of Earth's axis, and the precession or wobble of the axis, all of which affect how much sunlight reaches different parts of the planet at different seasons. The combination of these cycles creates a complex pattern of warming and cooling that acts like a climate pacemaker, but the cycles themselves are too weak to cause ice ages alone. They just trigger feedback mechanisms that amplify the changes. During the last glacial maximum about 21,000 years ago, ice sheets covered Canada, Scandinavia, Northern Europe, and parts of Russia and Alaska, containing so much water that sea levels were 400 feet lower than today. You could walk from France to England, from Alaska to Russia, from Australia to New Guinea, and from mainland Asia to Japan, all on dry land that's now ocean floor. The weight of these ice sheets was so enormous that it depressed the continental crust into the mantle, and these areas are still rebounding today, with Hudson Bay rising about half an inch per year as the land continues to bounce back from ice that melted over 10,000 years ago. The Laurentide ice sheet that covered most of Canada and the northern United States contained about 7 million cubic miles of ice and was over 2 miles thick at its center, creating its own weather systems and jet stream patterns. This massive ice sheet acted like a mountain range, forcing air masses around it and creating powerful winds at its edges that picked up fine rock dust ground by the glaciers and deposited it far from the ice as loess, incredibly fertile soil that now feeds billions of people. Some of the world's most productive agricultural regions, including the American Midwest, the Ukrainian steppes, and China's Yellow River Valley, owe their fertility to Ice Age winds that deposited this glacial flower. Life during the Ice Ages was dramatically different from today, with a mixture of familiar and bizarre creatures adapted to cold conditions that no longer exist. Woolly mammoths, with their long shaggy hair and curved tusks, roamed across the vast mammoth steppe that stretched from Spain to Canada, an ecosystem with no modern equivalent, part tundra, part grassland, maintained by the grazing of millions of large herbivores. These mammoths were so well adapted to cold that they had antifreeze proteins in their blood, small ears to minimize heat loss, and a hump of fat for energy storage, basically walking Arctic survival machines that thrived in conditions that would kill modern elephants. The Ice Ages produced some of the largest land mammals that ever lived, including the giant ground sloth Megatherium, which stood 20 feet tall and weighed 4 tons, using massive claws to pull down tree branches. Cave bears were 30% larger than modern grizzly bears, Irish elk had antlers spanning 12 feet, and saber-toothed cats had fangs 7 inches long specifically evolved to pierce the thick hides of mammoth calves and other megafauna. The gigantism of Ice Age mammals might have been an adaptation to cold following Bergmann's rule, which observes that animals in colder climates tend to be larger because bigger bodies retain heat better due to their lower surface area to volume ratio. Humans evolved during the Ice Ages, and the challenging, variable climate may have been a key driver of our evolution, selecting for intelligence, adaptability, and cooperation. The expansion and contraction of ice sheets created constantly changing environments that favored hominins who could adapt quickly, use tools, control fire, and work together in groups. Our ancestors had to deal with advancing glaciers, changing sea levels, shifting vegetation zones, and migrating prey species, challenges that required planning, innovation, and the ability to pass knowledge between generations. Neanderthals were the ultimate Ice Age humans, evolving in Europe during glacial periods and developing bodies perfectly adapted to cold climates with short, stocky builds that conserved heat and large noses that warmed incoming air. They survived through multiple glacial cycles for over 300,000 years, far longer than our species has existed, hunting mammoths and other large game with sophisticated weapons and strategies. Recent evidence suggests they were far more sophisticated than previously thought, creating art, using medicinal plants, and possibly even speaking complex languages, making their extinction around 40,000 years ago even more mysterious. The Ice Ages created refugia, isolated pockets of favorable climate where species could survive during glacial periods, leading to rapid evolution and the development of endemic species found nowhere else. Southern Europe, particularly the Iberian, Italian, and Balkan peninsulas, served as refugia for temperate species during glacial periods, while Beringia, the land bridge between Asia and America, was a refugium for cold-adapted species. These refugia acted as evolutionary laboratories, producing new species and subspecies that would later recolonize areas when the ice retreated, explaining much of the modern distribution of plants and animals. Sea level changes during ice ages repeatedly connected and isolated land masses, allowing species to migrate between continents and then evolve in isolation when sea levels rose again. The periodic connection of Britain to continental Europe explains why Britain has the same native mammals as France, while Ireland, which was cut off earlier, has fewer native species. Australia's unique fauna evolved in isolation after it separated from Antarctica, but during ice ages, lower sea levels connected it to New Guinea, allowing species exchanges that explain the presence of kangaroos in New Guinea and cassowaries in northern Australia. One of the most dramatic features of Ice Age climate was the occurrence of Heinrich events, massive discharges of icebergs from the Laurentide ice sheet into the North Atlantic that happened roughly every 7,000 years. These armadas of icebergs, containing enough fresh water to raise global sea levels by several feet, would melt and create a fresh water lid on the North Atlantic, shutting down the ocean circulation that brings warm water north. The result was rapid cooling in the northern hemisphere and dramatic changes in rainfall patterns globally, showing how instabilities in ice sheets can trigger abrupt climate changes that affect the entire planet. Even more abrupt were Dansgaard-Oeschger events, rapid warming episodes during glacial periods when temperatures in Greenland would rise by up to 15 degrees Celsius in just a few decades. These events, recorded in ice cores as dramatic shifts in oxygen isotope ratios, show that Ice Age climate was far from stable, flipping between cold and warm states like a flickering light switch. The cause of these rapid changes is still debated, but they likely involve changes in ocean circulation, ice sheet dynamics, and atmospheric patterns that created tipping points in the climate system. The Younger Dryas, occurring about 12,900 years ago just as the last ice age was ending, was a sudden return to glacial conditions that lasted about 1,200 years. In just a decade, temperatures in the North Atlantic region dropped by up to 15 degrees Celsius, glaciers started advancing again, and forests were replaced by tundra, all just as human civilizations were beginning to develop. This event was possibly triggered by the drainage of Lake Agassiz, a massive glacial lake in North America, which dumped enormous amounts of fresh water into the Atlantic and shut down ocean circulation. The end of the Younger Dryas was even more dramatic than its beginning, with temperatures rising by 10 degrees Celsius in possibly as little as 3 years, a rate of warming that would be catastrophic if it happened today. This impossibly rapid warming shows that Earth's climate system has tipping points where small changes can trigger runaway feedbacks that completely reorganize global climate in the span of a human lifetime. Ice cores from Greenland show that the transition from glacial to interglacial conditions involved a doubling of snow accumulation in just 3 years and a 50% decrease in dust in the atmosphere in less than a decade. As ice sheets melted at the end of the last glacial period, they released enormous floods that carved massive channels still visible today, including the channeled scablands of Washington state created by the catastrophic draining of glacial Lake Missoula. This lake, held back by an ice dam, contained as much water as Lake Erie and Lake Ontario combined, and when the dam failed, it released a flood with 10 times the combined flow of all rivers on Earth today. The flood waters, moving at 65 miles per hour and carrying icebergs the size of buildings, carved channels hundreds of feet deep in solid basalt bedrock in a matter of days, showing the incredible erosive power of glacial meltwater. The melting of Ice Age glaciers created most of the lakes in northern regions, from the Great Lakes of North America to the thousands of lakes in Finland, Sweden, and Canada. Minnesota alone has over 10,000 lakes, almost all created by glacial action, either carved by moving ice, formed in depressions left by melting ice blocks, or dammed by glacial deposits. The Finger Lakes of New York were carved by glaciers that followed existing river valleys, deepening them into long, narrow lakes, while kettle lakes formed where chunks of glacial ice were buried in sediment and later melted, leaving behind water-filled depressions. Glaciers also created much of the spectacular mountain scenery we see today, carving U-shaped valleys, cirques, arêtes, and horns like the Matterhorn through a process called glacial erosion. Yosemite Valley, with its sheer granite walls and hanging valleys where tributary glaciers once joined the main glacier at different levels, is a textbook example of glacial landscape modification. Fjords, those spectacular narrow inlets surrounded by towering cliffs found in Norway, Alaska, and New Zealand, are glacial valleys that were flooded by rising sea levels when the ice melted. The weight of Ice Age glaciers created features called drumlins, streamlined hills shaped like inverted spoons that show the direction of ice flow and are found in vast fields across formerly glaciated regions. Central Park in New York City is built on drumlins and other glacial features, with exposed bedrock showing scratches called glacial striations that indicate the ice moved from north-northwest to south-southeast across Manhattan. Long Island itself is essentially a pile of glacial debris, a terminal moraine marking the southern limit of the ice sheet, showing how glaciers literally built the landscape of many modern cities. Icebergs calving from Ice Age glaciers carried rocks far out to sea, dropping them as they melted and creating layers of ice-rafted debris that scientists used to track past ice sheet behavior. These Heinrich layers, named after the scientist who discovered them, contain distinctive red-colored rocks from Hudson Bay that can be found in ocean sediments as far away as Portugal. By analyzing these layers, scientists can determine when ice sheets became unstable and released armadas of icebergs, providing a record of Ice Age climate instability preserved in ocean mud. The Ice Ages had profound effects on ocean chemistry, with colder water able to hold more dissolved gases including carbon dioxide, which helped lock away atmospheric CO2 and maintain cold conditions. During glacial periods, the deep ocean stored much more carbon than today, acting as a massive carbon sink that kept atmospheric CO2 levels around 180 parts per million compared to over 400 parts per million today. This oceanic carbon pump was enhanced by increased dust deposition on the ocean surface, which fertilized phytoplankton with iron and other nutrients, increasing photosynthesis and carbon burial. Ice Age dust, generated by glaciers grinding rocks and strong winds blowing over exposed continental shelves, was up to 25 times more abundant than today and had major effects on climate and ecosystems. This dust, rich in minerals, fertilized oceans and rainforests far from its source, with Saharan dust fertilizing the Amazon rainforest and Asian dust fertilizing the Pacific Ocean. Ice cores from Antarctica contain dust from Patagonia, while Greenland ice cores contain dust from Asian deserts, showing that Ice Age winds created a global dust transport system that connected distant parts of the planet. The Ice Ages fundamentally shaped human culture and technology, forcing our ancestors to develop clothing, sophisticated shelters, food storage techniques, and complex social cooperation to survive in harsh periglacial environments. The need to survive Ice Age winters may have driven the development of language, art, and religion as ways to preserve and transmit crucial survival knowledge across generations. Cave paintings from the Ice Age, found from Spain to Indonesia, often depict the large animals that humans hunted and may have served as teaching tools or magical attempts to ensure hunting success. The end of the last Ice Age coincided with the development of agriculture, and this may not be coincidental as the stable climate of the Holocene interglacial made agriculture possible for the first time. During glacial periods, climate was too variable and CO2 levels were too low for productive agriculture, but the warmer, more stable Holocene created conditions where humans could reliably grow crops year after year. The transition from hunting and gathering to agriculture happened independently in multiple locations around the world within a few thousand years of the Ice Age ending, suggesting that climate was a controlling factor. Many of the world's great rivers follow courses determined by Ice Age meltwater, including the Mississippi River, which was fed by the melting Laurentide ice sheet and carved its current valley during glacial melt periods. The Ohio and Missouri rivers mark the approximate southern boundary of Ice Age glaciation, flowing along the front of the former ice sheet where meltwater collected. The Columbia River Gorge was carved by repeated Ice Age floods, while the Thames in London follows a course forced southward by advancing ice that blocked its original route to the North Sea. The Great Lakes of North America, containing 21% of the world's fresh surface water, are perhaps the most impressive legacy of the Ice Ages, carved by glaciers and filled with their meltwater. These lakes are still adjusting to the end of the Ice Age, with post-glacial rebound causing the land to tilt, making water levels rise in the south and fall in the north. Lake Superior, the largest freshwater lake by surface area, is so vast and deep that it contains enough water to cover all of North and South America to a depth of 1 foot. Ice Ages created land bridges that allowed massive migrations of species and peoples, fundamentally shaping the distribution of life on Earth, including humans colonizing the Americas via Beringia. The Bering Land Bridge wasn't just a narrow connection but a vast region the size of Texas that existed for thousands of years, supporting its own unique ecosystem of grasslands and tundra. Humans crossing Beringia brought with them dogs, technologies, and knowledge adapted to Arctic conditions, but they had to wait thousands of years for an ice-free corridor to open between the Laurentide and Cordilleran ice sheets before they could migrate south into the Americas. The Ice Ages are recorded in extraordinary detail in ice cores from Greenland and Antarctica, which preserve annual layers of snow going back hundreds of thousands of years like frozen history books. Each layer contains information about temperature, atmospheric composition, volcanic eruptions, dust levels, and even solar activity, providing a year-by-year record of climate change. The oldest ice core from Antarctica goes back 800,000 years and shows that atmospheric CO2 levels during all that time never exceeded 300 parts per million until the Industrial Revolution, when humans began burning fossil fuels. Tree rings, lake sediments, coral growth bands, and cave formations all preserve records of Ice Age climate, allowing scientists to reconstruct past conditions with remarkable precision. Stalactites and stalagmites in caves grow faster during wet periods and contain oxygen isotopes that record temperature, creating climate records that can be dated using uranium decay. Pollen preserved in lake sediments shows how vegetation changed as climate shifted, with forests replaced by tundra during cold periods and vice versa during warm periods, creating a botanical history of the Ice Ages. The study of Ice Ages led to the discovery of greenhouse gases and their role in climate, as scientists puzzled over what could cause such massive climate changes. In the 1850s, Joseph Fourier realized that something in the atmosphere must trap heat, and John Tyndall identified water vapor and CO2 as greenhouse gases that could explain Ice Age cycles. Svante Arrhenius in 1896 calculated that doubling atmospheric CO2 would warm Earth by 5 to 6 degrees Celsius, remarkably close to modern estimates, and suggested that changes in CO2 could explain Ice Ages. Ice Ages demonstrate the concept of climate tipping points, where small changes can trigger massive feedbacks that completely reorganize Earth's climate system. The ice albedo feedback, where white ice reflects sunlight and causes cooling that creates more ice, can run away in both directions, either covering the planet in ice or melting it all. The carbon cycle feedback, where warming oceans release CO2 which causes more warming, shows how initial small changes can be amplified into major climate shifts that last thousands of years. During Ice Ages, the jet stream was pushed southward by the presence of massive ice sheets, bringing Arctic weather much farther south than today and creating different storm tracks. California was much wetter during Ice Ages, with massive lakes filling valleys that are now deserts, including Lake Bonneville in Utah, which was the size of Lake Michigan. Death Valley, now one of the hottest and driest places on Earth, contained a lake 600 feet deep during the last ice age, showing how dramatically precipitation patterns can change. The Antarctic ice sheet, which contains 90% of Earth's ice and 70% of its fresh water, began forming 34 million years ago and has survived through multiple warm periods. If the entire Antarctic ice sheet melted, global sea levels would rise by about 200 feet, flooding every coastal city on Earth and displacing billions of people. The ice sheet is up to 3 miles thick in places and contains ice that fell as snow over 1 million years ago, making it Earth's oldest ice and a unique archive of ancient climate. Greenland's ice sheet, containing enough ice to raise sea levels by 24 feet if it completely melted, is much younger than Antarctica's, forming only about 3 million years ago. The Greenland ice sheet has survived previous interglacials warmer than today, but it's now losing mass at an accelerating rate due to human-caused warming. Scientists have discovered that the base of the Greenland ice sheet is melting from geothermal heat, creating vast networks of under-ice rivers and lakes that affect how fast the ice moves toward the sea. Ice ages show that Earth's climate is bistable, capable of existing in either a warm state or a cold state, with relatively rapid transitions between them. The difference in global average temperature between a glacial period and an interglacial is only about 5 degrees Celsius, showing how sensitive climate is to small changes. This means that human activities, which have already warmed the planet by over 1 degree Celsius, are significant on the scale of natural climate changes that have dramatically altered Earth's surface. Some scientists believe we should currently be entering a new glacial period based on Milankovitch cycles, but human CO2 emissions have overwhelmed the natural cooling trend. The amount of CO2 humans have added to the atmosphere is enough to delay the next glacial period by at least 50,000 years and possibly up to 500,000 years. This means humans have become a geological force comparable to the orbital cycles that have controlled climate for millions of years, fundamentally altering Earth's natural climate rhythm. The ice ages left behind massive aquifers of pristine water trapped in underground sediments, which billions of people now depend on for drinking water and agriculture. The Ogallala Aquifer under the Great Plains, one of the world's largest aquifers, was filled with ice age meltwater and is now being depleted faster than it can recharge. This fossil water, some of it tens of thousands of years old, is essentially a non-renewable resource from the ice age that we're rapidly exhausting. Permafrost, permanently frozen ground covering 24% of the northern hemisphere land surface, is a remnant of the ice ages that contains twice as much carbon as the entire atmosphere. As permafrost thaws due to current warming, it releases methane and CO2 that have been locked away since the Ice Age, creating a feedback loop that accelerates warming. Some permafrost in Siberia and Alaska has remained frozen for over 700,000 years but is now thawing for the first time, releasing Ice Age carbon back into the atmosphere. Ice Age animals frozen in permafrost, including mammoths, cave lions, and even puppies, are so well preserved that their DNA can still be extracted and potentially used for de-extinction efforts. Scientists have found mammoth carcasses with liquid blood, intact organs, and even their last meals preserved in their stomachs, providing unprecedented insights into Ice Age life. The possibility of bringing back extinct Ice Age animals using CRISPR and other genetic technologies raises ethical questions about whether we should resurrect species that went extinct naturally. The Ice Ages created evolutionary bottlenecks where populations were reduced to small numbers, accelerating evolution and creating new species through founder effects and genetic drift. Polar bears evolved from brown bears during an ice age about 600,000 years ago when a population became isolated by ice and adapted to Arctic conditions. Humans went through a severe bottleneck about 70,000 years ago, possibly due to ice age climate stress, when our entire species may have been reduced to fewer than 10,000 individuals. Studies of Ice Age climate have revealed that current global warming is happening faster than any natural climate change in the geological record except for asteroid impacts. The rate of CO2 increase today is about 100 times faster than the increase that ended the last ice age, giving ecosystems and species little time to adapt. Temperature increases that took thousands of years at the end of ice ages are happening in decades today, making current climate change unprecedented in the context of ice age cycles. Ice sheets have their own weather systems, creating katabatic winds that can exceed 200 miles per hour, the fastest winds on Earth outside of tornadoes. These winds, caused by cold, dense air flowing down the ice sheet under gravity, sculpt the ice surface and transport massive amounts of snow, creating features like sastrugi, wave-like ridges that can be taller than a person. The sound of these winds on the Antarctic ice sheet has been described as otherworldly, a constant roar that early explorers found deeply unsettling. The color of Ice Age ice tells a story, with clear blue ice indicating slow accumulation and few air bubbles, while white ice formed quickly and trapped more air. The deepest, oldest ice in Antarctica is so compressed that it's crystal clear and harder than concrete, requiring special drills with diamond bits to penetrate. When this ancient ice is brought to the surface and melts, it releases air that hasn't been in the atmosphere for hundreds of thousands of years, literally allowing scientists to breathe Ice Age air. Ice ages may have played a crucial role in the development of complex life, with Snowball Earth events potentially triggering the evolution of multicellular organisms. The stress of global glaciation could have created evolutionary pressures that favored cooperation between cells, leading to the first multicellular life. The end of Snowball Earth events brought massive amounts of nutrients into the oceans as glaciers ground up continental rocks, potentially fueling the Cambrian explosion of complex life. The transition between ice ages and warm periods shows that climate change isn't gradual but happens in steps and jumps, with the system resisting change until a threshold is crossed. Ice sheets don't melt uniformly but collapse in stages, with periods of rapid melting separated by pauses, making sea level rise episodic rather than smooth. This punctuated pattern of climate change means that future warming might not be gradual but could involve sudden shifts to new climate states. The ice ages show that small changes in Earth's orbit can have massive effects on climate when amplified by feedbacks, demonstrating the delicate balance of our planet's climate system. A change of just a few % in summer sunlight at high northern latitudes can trigger the growth or collapse of ice sheets covering millions of square miles. This sensitivity means that human activities, which are changing atmospheric composition more than orbital cycles ever have, could trigger similarly dramatic changes. Ice Age floods carved some of Earth's most spectacular landscapes, including the Grand Canyon of the Yellowstone and the Columbia River Gorge, showing the immense erosive power of meltwater. Glacial lake outburst floods in the Himalayas, caused by ice dams failing, continue to pose threats today and show that Ice Age processes aren't just ancient history. These floods can release billions of gallons of water in hours, traveling at highway speeds and carrying boulders the size of houses, demonstrating nature's raw power. The legacy of the Ice Ages extends to modern politics and economics, with the most developed nations being those in formerly glaciated regions with fertile soils and abundant fresh water. The arbitrary borders of many U.S. states and Canadian provinces follow features created by Ice Age glaciers, from rivers to moraines to the edges of former glacial lakes. Even the location of major cities like Boston, New York, and Montreal was determined by Ice Age geography, situated at sites where glaciers created natural harbors or left behind flat terraces suitable for development. As we face an uncertain climate future, the Ice Ages provide both warnings and hope, showing that Earth's climate can change dramatically but also that life is remarkably resilient. The fact that our species evolved during the ice ages and survived multiple glacial cycles shows that humans are incredibly adaptable, though our civilizations have never faced changes as rapid as those we're causing today. Understanding ice ages isn't just about the past but about recognizing that we live on a planet with a violently variable climate that has repeatedly reorganized itself, and that our current stable climate is both precious and precarious. The story of the ice ages is ultimately the story of change, of a planet that has been many different worlds over time, and knowing this history, we can better appreciate the world we have now and work to preserve it for future generations who will inherit whatever climate we leave them.